Hello and welcome to our lectures here. I just wanted to pop in, and I will be popping in occasionally during these recordings. You may even see me over here. Maybe you'll see me over there. I might even be in the background. You never know, I may be way over there. But I may pop in time to time to say hello during these lectures. But before you begin watching the first lecture, which is chapter 1 we have up today, I want to remind you of the proper things that you need to do to watch these lectures and get the most out of them. The first thing that you want to do is make sure that you find yourself over to our Canvas page. You might want to get it into the URL, which might be up there. Make sure you log on to our Canvas page and you'll find the module section. Within the module section, you'll find the handouts for each of these lectures. I can't tell you how important it is that you have these handouts with you, most likely printed out on a piece of paper that you can put on the desk there. And make sure that you are following along with your calculator. It's also really important, in addition to having the handouts present, to make sure that you do not forget to pause the video. I say pause, stop, wait on the video, especially when we're doing some examples. Whoa, a little out of sorts here. Let me fix myself. There we go. We want to make sure that you stop the video so that you can actually do the examples yourself before continuing on and seeing how our professor does it. This will give you great practice at doing the problems and not just watching our professor, who probably should be right about there in the videos coming up, do the examples. I would say that is the best thing that you can do. All right, with that, I will say bye-bye for now. We will throw it over to our professor. Hey, Mr. Professor, start the lecture.
Okay, everybody, welcome here to Chapter 1, An Introduction to Chemistry is the title. We're going to talk about several things in this chapter. We're going to talk a little bit about chemistry. We'll cover about the scientific method briefly. Then we'll get into really the heart here of Chapter 1, a little bit about matter, substances, mixtures. So let's get into it. Let's get into here Chapter 1. So Chapter 1 really... first off, opens up about talking about what chemistry is. And chemistry is really the science of matter, as it says there. Matter is really any object that occupies space and has mass. So those are two important parts, mass and occupies space. Essentially, that's going to be pretty much everything that you could think of that will have mass and does occupy space. A lot of what chemistry deals with is the study of matter and, how it changes, maybe goes from different states. So speaking of that, as we'll talk about more in some later chapters, there's really 3 states of matter that we deal with a lot. The first state of matter is the solid state. And in the solid state, everybody is pretty much packed in there, pretty tight to one another. The atoms, the molecules, there's not a lot of movement that's happening there. That's why, as we'll talk about, solids are pretty rigid. They sort of lock themselves into place because they're not very energetic. And that's a little bit different than what we see in the other state of matter, which is liquid. And in the liquid state of matter, we still have everybody packed in there relatively tight to one another. But there is a little bit more room for movement. So the molecules, the atoms, they're able to sort of pass one another. And that's why when we think about liquids, we think about it being fluid, as opposed to obviously solids, which doesn't really flow, right? They're hard, like a desk or whatever it may be. And we don't have that sort of fluidness that we have with a liquid. If we pour it obviously flows out of the container all over the floor. Hopefully we don't pour it on the floor or anything like that. The third state of matter is gas. And different than the other 2 states of matter, this is really the state of matter where pretty much everybody has broken apart from one another. They're flying around free from one another. As they're moving around, as we'll talk about in a later chapter, there are collisions that occur, and that is what we associate pressure a lot of times with gases. And we'll talk about a whole chapter on gases and basically the association of pressure with gases. Now, as we can see here, solid, liquid, and gas, a lot of what we deal with in chemistry deals with substances in those different states of matter. Also, a lot of what we deal with is the sort of transition of a substance from, say, one state of matter to the next. So, for example, as we go from solid to liquid, that is the process of melting. So, very common sort of example, right? If you had an ice cube and you take it out, it will start to melt, basically, right? And it will go through that melting process as it really picks up energy from the surroundings to make liquid water, right? And in that case, we could also, if we wanted to, take our liquid water and we could put it back in the freezer and go from the liquid state of matter, for example, to the solid state of matter through a process which is known as freezing. Now, if we took our liquid water and continued down the pathway there, we could go from liquid to gas, which is the process of evaporation or vaporization. There's also the process that's sort of the opposite effect. If we are starting in the gas and go back to liquid, we are in the process of what is known as condensation. In addition, we can transition actually directly from the solid, skipping the liquid part and ending up there in the gas phase. That is the process of sublimation. And we can go from gas, once again, skipping the liquid part to the solid part. That is the process of deposition. Like you're sort of depositing something onto a surface. For example, if you remember, maybe you're old enough to remember CDs, DVDs. If you ever seen one, they look very shiny up on top. That's sort of how they get it shiny. They deposit some metals on it. Again, it also skips the liquid phase, so it goes directly from gas back to solid. Again, skipping that whole kind of liquid phase cleanup in some cases. Now, a lot of what we deal with, as I mentioned, is these transitions going from, say, solid to liquid to gas, and also opposite, gas, liquid to solid. In addition, a lot of times what we look at, along with the different states of matter, what state they may be in, is the energy associated with doing these processes. So, for example, if we think about going from the solid state to the liquid state to the gas state, the question is, in terms of energy, do we need to put it in or take it out to do those processes? So why don't you take a second here, think about it as we go from solid to liquid to gas. Are we going to take those energy in to do that or out to do that? I'll give you a moment here to think about your answer. Now, hopefully your answer is, the survey says we actually has to put energy in to do that. So if we go back up here, for example, to our ice cube example, which is obviously in the solid state going to our liquid state and so forth, the ice cube picks up heat and energy from the surroundings, which means energy gets put in. And if we took our liquid water and we put it up on the stove there to make a little pasta for dinner, we put a fire underneath it. That is a finely drawn fire, our Bunsen burner. I know it appears to be a triangle with a line on it, which it is, but we'll just pretend it's a nicely drawn Bunsen burner there. Or if we heat it up there, that liquid water, we're obviously going to create steam, right? And steam is really the gas version there of water. And all those processes require energy to be put in, are sometimes referred to as energy being absorbed by the system. And those processes in chemistry are what are referred to as being endothermic. So when somebody says this is an endothermic process, our heat and energy is being absorbed. These are all processes where something is gaining energy. And in our case of our ice cube, again, it is gaining energy, and it is going to go from the solid phase. It's going to allow these molecules, for example, to have a little bit more energy, which means they can start moving around from one another to the liquid phase, and then gain even more energy to go off into the gas phase. That means that if we think about sort of the opposite of that, going in sort of the opposite direction, going from our gas phase to, say, our liquid phase down to our solid phase, this would require energy to be released, basically. And when we have processes where energy is being released in chemistry, this is what is referred to as being exothermic. So an exothermic process is when energy and heat is being released. And if you just think about what's happening, say, if we started over here at the gas phase, these guys are flying around really fast. So I'll just draw a couple of gas molecules up here. They're flying around really fast at this moment, moving around. If we remove energy from this and take energy out, what we're going to have with these gas molecules is now they're going to be flying around a lot slower, which means when they come in contact with each other, they no longer have enough energy to sort of bounce off one another and continue on into gas phase. They kind of, if you want to think about it, will clump together. And when they clump together, they're just going to drop back out into the liquid phase. And if we continue to remove energy from those processes, our molecules, they will no longer have enough energy even to pass one another, which is sort of what's happening in the liquid phase. And then they're going to really, for a lack of a better description, kind of lock themselves into place here in the solid phase as they go backwards. So in all these processes here, energy is a really important component in terms of chemistry of what we look at. And as you go from solid, liquid to gas, those are endothermic processes. Energy is being put in to, say, something like water to do that. And as we start in the opposite direction, going from gas to liquid to solid, we got to release that energy to allow everybody basically to slow down and not continue to move around as fast. Now, a couple other important things about this, also things to keep in mind. For example, the process of melting and freezing, does this happen at the same temperature or different temperature? So why don't you take a moment and think about what your answer is to that? So if you think about what is happening, it actually occurs at the same temperature. So the process of melting and freezing actually occur at the same temperature. If we're talking about water, for example, what we've been talking about here, which is our water, this is going to be 0 degrees Celsius is the normal melting point and freezing point for water. So at exactly, for example, 0 degrees Celsius, you actually have both phases happening at the same time. You have kind of like ice crystals. So you got a little bit of solid, you got a little bit of liquid. It's really not until you get a little bit above 0 degrees that you fully sort of transition into the liquids phase. And it's not until you get a little bit low 0 degrees that you transition into the solid phase. But exactly 0 degrees Celsius, you basically have both phases happening at the same time. Now, when we think about the other sort of transitions that occur as well, evaporation and vaporization and condensation, that also is going to occur at the same temperature. And for water, that's going to be its normal boiling point, which is 100 degrees Celsius is the normal boiling point of water. So once again, as we go from our gas to liquid to solid, we're releasing that energy. And again, exothermic is the process that involves energy being released. Endothermic are processes and heat and energy involves energy being absorbed. So a lot of times we look at those two major things. We look at structure properties. We look at energy associated with what's happening with matter. We look at how it's transitioning perhaps from one state to the next. We obviously, as it says up there before, I scribbled all over the page there. We looked at, we do experiments to sort of see what is happening here. Now, just a point about sort of that idea of you put something back into the freezer and it's like losing energy. And sometimes people have maybe a hard idea or understanding of that. But if you think about what happens in terms of energy, for example, when you take your water and you pop it into the freezer, take your liquid water, just flowing around in a container, hopefully, into your freezer. Now, heat and energy, heat flows from hot to cold. So heat always sort of flows from hot to cold. So the hotter item will basically lose energy to the colder substance. The colder substance temperature will rise. The warmer guy's temperature will come down. And again, as we'll talk about when we talk about energy, if they're sort of in an insulated container, they'll meet somewhere in the middle. So when you think about putting your water into a freezer, the freezer is obviously much, much colder than the water that you put in there. And that means that in terms of the water, it's actually going to be exothermic. It's going to release its heat and energy actually to the surroundings in the freezer as it's a colder temperature. So the water that you put in there actually is going to exothermically lose its energy. The result of that is the water will lose energy, and before you know it, now you got solid ice cubes that have formed. So in chemistry, we do try to understand how and why chemical changes occur in nature. Chemical changes are really, as we'll talk about, chemical reactions. And there's really kind of two things that we look at when we're dealing with sort of what is happening. There's sort of what we can see with our sort of naked eye, if you will. That's the macroscopic world, the kind of the big picture, if you will. There's also things that we really can't see what's going on, which is sort of happening, if you want to think about behind the scenes, on the microscopic sort of world. And that is what we can see, but that's sort of what's really happening with atoms and molecules. Now, when we do something, for example, in a reaction, and we do some type of chemical reaction, oftentimes there are two parts to a chemical reaction, as we'll talk about in a later chapter. There are the reactants, and they go to the products. And the reactants are our starting materials, and our products are basically what is formed as a result of the chemical reaction. So when we do some type of reaction, maybe we take two solutions together, and both of these solutions are made up of ions, which are positive and negatively charged particles that are floating around in the solution. And when we pour these guys together and we put it into, say, a beaker or something like that, we end up getting, maybe we'll go with a nice green solid, since that's the color I got on my marker here. And we make this green solid formed as a result of that, which is known as a precipitate. So that is definitely a macroscopic sort of example of what's happening in this reaction. This would be what is sometimes referred to as a precipitation reaction, as a solid is formed. And we could definitely see that with our naked eyes. But, what is really happening to form that solid? Well, what is happening to form that solid, for example, is when we put into our beaker each of those solutions, we'll just call this solution A. When solution A goes for a swim, we'll have some positively and negatively charged ions in the solution. And when we put in the other solution, we'll call that solution B. And I'll make it blue now, just to sort of distinguish it between the other solution. bluish here. So now when we put solution B into the mix here, we get some positive and negative things, our ions floating around that solution. And what happens in this thing that we maybe cannot see microscopically is these ions, when they come together, certain combinations of ions will come together and actually form a solid. And here, for example, this positive guy will come together with the negative guy here. And that is the result of the solid that we see form in this reaction. We still have our other ions basically still floating around in that solution freely, that again, we can't necessarily still see. We have a positive ion still floating around. We also would have a negative ion floating around as well. We can't see those ions that are still floating around. The only thing that we can see in the big picture is we got a solid that formed. So a lot of times there are signs that we could see with our sort of naked eye of, oh, something happened here. But a lot of times in chemistry, there's a lot of things that we cannot see, like those ions still floating around in the result of that sort of reaction. In addition, there's a bunch of reactions when we just kind of clear out a little bit of some room here. There's some reactions that are what are referred to as reversible reactions, which actually can head in both directions. And in a reversible reaction, you will see not one arrow, but you'll actually see two arrows in a reaction or an equation. And that implies that there's a forward direction, which in that reaction is our reactants that go to products. And there's a reverse direction where some of those products will actually recombine and make some more reactants of what we sort of started with. So when we have this type of reaction, we sometimes will see the reaction and we'll do it. And we'll just say here, once again, we did this reaction. We made this nice greenish solution. And maybe again, we started with these two sort of solutions. We poured them together. We didn't get a solid this time. We actually just got it went from maybe a colorless solution to a green solution, for example. And at this point, we look at the beaker and go, well, it's green. Sounds nice. Not much is happening at this point. The reaction's over. There's nothing else happening. And to our sort of big picture, our sort of naked eye looking at this beaker and it's green, we would say, yeah, it's over. The reaction's done. Nothing's happening. But if we were able to super zoom into this reaction, let's just say, for example, we had A plus B went to C plus D. And in this reaction, what we would see is if we were able to super zoom in here, although it looks to us in the beaker that the reaction's over, it's still green, nothing else is changing, it's just maintaining that green sort of color, we would see a lot of activity. We would actually see a lot of A and B guys going to C and D. We would also, if we were able to look in there, be able to see some of the C and D going backwards and going to A and B. So this type of reaction, which is sometimes referred to as reaching equilibrium, that means the rate of the forward reaction equals the rate of the reverse reaction. And ultimately, because they're going back and forth at the exact same rate, everybody locks themselves into place. And although to our naked eye, when we look at the beaker, it looks like, well, it's over. Nothing much is happening. But if we were able, again, to super zoom in to the molecular level, the microscopic level, there is a lot of activity that's constantly happening that we can't see. And we could only see sort of the big picture of, oh, it's this green solution is staying this green solution. The color is not going away. It's basically able to maintain that. So a lot of what we see, there are certain reactions where it is just a one-way street, where we have the reaction occur and we form perhaps a solid and the reaction is done. There's also a lot of reactions, for example, where it may appear to be over and nothing's happening, but there actually is still a lot of activity happening back and forth. Now, again, in my first example there where we had the sort of precipitate, that's sort of like a one-way street, for example. And in those type of reactions, pretty much everybody's going over to the product side, there's nobody coming back the other way. So again, these reversible reactions do have those two arrows. They have two directions. But I'm just using this as an illustration of it may appear on the big picture to be done, but there is a lot of activity if you could look at sort of what's happening on the molecular level. And that's a lot of what we try to look at in chemistry, is what's happening both on sort of the big picture and what's sort of happening behind the scenes on the microscopic level of sort of atom-wise, molecule-wise of what's going on. Same idea, for example, if we think about a water molecule. And when we think about water, right, what does it look like? And your answer may be, well, I think of water as, hopefully not green, but liquid water looks something like this, right? But if we were to look at water and we're able to somehow grab out one molecule of water by itself and hold it in our hand, water will look something like this, which is two elements together, hydrogen and oxygen, and it is H2O. The water molecule here is actually held together by sharing of electrons. And that is what is referred to, as we'll talk about, as covalent bonding. So one individual water molecule is actually held together by the sharing of electrons between the oxygen and the hydrogen. So for example, this hydrogen is going to share a couple of electrons with the oxygen, and the oxygen in the middle will actually share a couple of electrons with both of the hydrogens there. And that is essentially what holds that water molecule together. Now, the actual sort of microscopic view of a water molecule looks like this. The macroscopic view of a water molecule looks like, now that I got blue, I guess that would be a better way to use it. Looks hopefully something like that. It looks like, just obviously liquid water. Now, clearly when we have a cup of water, you take a little bit of water out of the faucet, whatever it may be, it's not just one single water molecule there. There is a lot of water molecules that are present. So obviously on the macroscopic world, it is going to appear very different than on the microscopic world where you can zoom in. So let's talk a little bit about the scientific approach and sort of the scientific method. So a lot of the scientific method really involves sort of several steps to it. First step is to collect facts and data relevant to your question. And really, in a lot of cases, it all starts with an observation. And an observation about you saw something occurring, something is happening, and you wonder, why does that happen? Perhaps you're working for somebody and you say, hey, I observed this happening. And they'll say, that's a nice observation. Why don't you go figure out maybe why that is happening? So a lot of times when we do some type of observation, it raises some questions about what is happening, and we try to formulate a hypothesis. And a hypothesis, a real good hypothesis, is a tentative explanation for what we're observing. And a really important aspect of that, especially in chemistry and the sciences, is oftentimes a testable sort of explanation, some type of explanation where you can do some type of experiments to either verify your hypothesis or sort of test your hypothesis. Then we typically will do experiments, and that usually will lead, unfortunately, to a couple of things. So we have an observation, we do a hypothesis, we do some experimentation, and usually at that point, it will oftentimes lead to more observations. Maybe you got some observations about what you originally saw. Maybe you observed some other sort of things happening along the way. Usually that will lead you back to your hypothesis to either revise it, come up with another hypothesis that you can test, and you go do some more experiments. Speaking of working for somebody, they will oftentimes say, oh, that's really good, you found that, but you also observed this. Why don't you go figure out why that's happening, right? And it can end up being maybe a vicious sort of cycle here as you kind of keep going around and around. Eventually, hopefully, your experimentations and stuff will lead really to one of two things. It may lead to something that's known as a theory. It may also lead to something that is known as a law. And there is some differences between a theory and a law and sort of what those two things mean. So let's talk a little bit about each of those. A theory is a well-established hypothesis that will sort of lead to a theory that summarizes what is occurring. Now, one of the main sort of aspects of a theory is the idea that it can explain what is happening to sort of the best of the ability of the experiments that were performed. When a theory, you may end up finding that maybe not all aspects of it is correct. There are maybe some parts that could be proven not to be correct through later experiments. So later experiments may actually disprove some parts of it and may also reinforce other parts to it. But it can be revisited, revised, if you will. And that's different than a law. A scientific law is one that no matter what happens, it always happens under those given conditions. So there's no exceptions. There's sort of no revisiting it. There's no little asterisk of, well, in this case, never mind. It won't work so well, but in this case, it does work. So with a law, it doesn't matter sort of the situation. There's no exceptions. It will always basically happen the same way. So what are sort of differences here? For example, there's the Dalton's law, Dalton's atomic theory. Dalton's atomic theory was believed to be correct in all aspects of it. There's kind of 4 parts to it. Over the years, other experiments and ideas have led to the idea that there are a few parts of it that are incorrect. There's a couple things that are not correct about it. Bohr's theory of the hydrogen atom, which was thought to work really well, explains things very nicely for hydrogen. But further experiments and ideas found that as you moved away from hydrogen, it did not work so well. So it worked only well to explain what's happening with hydrogen, but there's a lot of other elements that it doesn't work so well about. Now, when we talk about something like a law, for example, there's the law of conservation of energy. So the conservation of energy is the idea that we don't create nor destroy any energy along the way. We can't transform energy from one form to the next, but we don't create it nor destroy it. And a lot of what we deal with in chemistry and the idea of how energy moves from one object to the next is in a sort of perfect sort of manner. So for example, here we have, for example, a system. The system can be anything that you're dealing with. It could be like the beaker you're doing the experiment in. Could be the test tubes that you're doing the experiment in. And then pretty much everything outside of that is the surroundings. So for example, if a system, or if you do a chemical reaction, for example, in a test tube, and it gives off energy, let's just say it gives off 5 kilojoules of energy. We're not going to lose that 5 kilojoules of energy. It is going to be the surroundings that are basically going to say, thank you very much. And they're going to pick up that 5 kilojoules of energy. Now, when we think about what's happening in terms of energy, as we just talked about a little bit a second ago, for the system, it's going to be an exothermic process. It's going to lose or give off that energy of 5 kilojoules. But when we think about the surroundings, it's going to be actually an endothermic process for the surroundings. It's going to absorb that energy from the system. Net result is we didn't lose any energy. We didn't create any new energy. We just transferred the energy from one side to the next. Another idea of a law is the law of conservation of mass. And that also says something like we don't create nor destroy matter in a chemical reaction. And that's why, if you might be familiar with, or you will be when we get to that chapter, if we do some type of reaction where we take something, say like methane, and we react it with some oxygen, And on the other side there, we make a little carbon dioxide and some water. A lot of times when we do a chemical reaction or equation like this, we always have to balance it. In this case, if we're going to balance it, we'll do a little 2 in front of the water. That means we'll also do a little 2 right there in front of the oxygen. And what that means is in this chemical reaction, if we started with, as we can see here on the left-hand side of the arrow, we have 1 carbon, which is this guy right there. We have 4 hydrogen atoms, which is these 4 right there. We also have 4 oxygen atoms, which is the 2 in front times the 2 there. Again, that 2 in front means that we have basically 2 of these oxygen molecules. So that's 2 oxygens there, and 2 more there makes 4. We go on our product side here of what we made. We have 1 carbon atom. We have 2 times 2 is 4 hydrogens, and we have 2 oxygens there, and 2 times 1 is our 4 oxygens there. And by the way, the 2 in front of the water means, as I drew water earlier, we have basically 2 molecules of water. That is our 1, 2, 3, and 4 hydrogen atoms. That is our 1 and 2 oxygen atoms. And our CO2 looks like this. And that is our 3 and 4 oxygen atoms that are there as well. Now, in this particular case, when we look at this, we didn't lose any elements along the way. And that's the idea of the conservation of mass. We had 1 carbon we started with, we ended with 1 carbon. We had 4 hydrogens we started with, we ended with 4 hydrogens. And we had 4 oxygens we started with, we ended with 4 oxygens. The only difference is where everybody ended up. They ended up actually in different locations, if you will. They're hooked up differently than what they started with. But element-wise, we never lost any element along the way, so we did not lose any mass. So what does that mean? It means really here, carbon is 1201 in terms of its mass. Hydrogen is about 1.008, oxygen 16. That means that we had the exact same number of those elements on each side, which means we have the same mass we started with in terms of the elements and the same mass of those elements that we finish with. So that is the law of conservation of mass, which means no matter what you do in any chemical equation, chemical reaction, you will always conserve those elements. It's only in nuclear reactions, which we don't necessarily cover too much in this class, you will in a later chemistry class probably, that you actually don't have that conservation of elements, but this law of conservation of mass for chemical reactions is definitely the case. We always end up with and start with the same elements. They just end up in different places. That's essentially what a chemical reaction is. It's a chemical change. What we start with and what we end up with are fundamentally different things, but they are made up of the same elements. So let's talk a little bit about matter. Matter, as I mentioned, is pretty much what everything's made up of. And on the microscopic level, pretty much all matter is composed of atoms. Atoms are made up of, as we'll talk about in a later chapter, protons, which are positively charged particles, electrons, which are negatively charged particles, and neutrons, which have basically no charge. And atoms are the basic unit of elements. And elements are pretty much what everything is made up of. It's sort of the basic building blocks of everything, as we'll talk about in a bit. Elements you could think of again as sort of like the alphabet. Different combinations of elements give us different molecules, our compounds, and different substances. So the 3 states of matter, as we talked about there, we have our solid state, which in the solid state, it has a definite shape and volume, and it's independent of the container it's in. In most cases, things in their solid state are very, very tight to one another. They're packed very dense to one another. They're rigid. there's not a lot of energy, so that's why they're kind of just lock into place with each other, because they don't have a lot of energy. One very common or important exception actually is water, which is what this picture is here. Water is one of the few substances where in its solid state, it's actually less dense than in its liquid state. So most things in its solid state are much more dense and much tighter together. Water is actually an example of something that doesn't do that. Actually, in its solid state, the water molecules don't get as close as they can to one another. And that's because of what is referred to as hydrogen bonding that occurs between different water molecules. And we'll talk about that in a later chapter. They are very rigid. They're hard to change the shape of. Most solids have a very regular internal pattern. There are some solids which don't have that. So a lot of crystalline solids, for example, have a very ordered arrangement of how they're put together. Things like sodium chloride, salt, ionic compounds, they have very long range order. What that means is essentially in a crystalline solid, you could just take a little snippet of sort of the three-dimensional structure, and it's so regularly ordered that you could actually just rebuild the entire solid structure from it because it repeats in repeatable sort of patterns. There are some that don't have that sort of repeatable pattern shape, and that's what's sometimes referred to as an amorphous solid. And those have sort of a pattern that really no pattern at all. It doesn't have a repeatable sort of pattern and stuff like that. So things like glass and stuff like that, or those type of amorphous solids. Liquid is something that has a definite volume, but not a definite shape. So something that's a liquid has a definite volume, but not a definite shape. Typically here in the liquid, we have a little bit more energy. As we mentioned a little bit earlier, things are still relatively close to one another, but they do have a lot more energy. So there's a lot more motion. Again, why liquid guys are fluid. Liquids will typically take the shape of the container they're in. So what does it mean it has a definite volume but not a definite shape? Let's just say we had 10 milliliters of water in a test tube, for example. And if I took that 10 milliliters of water in that test tube and I poured it into a really big, wide trash can, and I poured it into there, I would then have 10 milliliters of water that has taken the shape of my trash can. If I took it out of the trash can and I put it into like a flask that has this sort of shape, my water then have basically this shape. If I put it into one of those silly straws, my best silly straw drawing looks like a curvy line, I suppose. There we go. My very bad silly straw drawing here. If I put it into the silly straw here, it's obviously going to take the shape here of the silly straw. Now, what it means by not a definite shape is obviously in the first container, it takes the shape of that, takes the shape of that container, takes the shape of that container, and obviously takes the shape of that container. As long as I'm not a klutz or anything like that, and I don't drop any of it along the way, which hopefully you don't, if you successfully transfer the water from this container to this container, to this container, to this container, you will still have 10 milliliters of water regardless, again, as long as you didn't drop it anywhere along the way. The last state of matter there is our gas state of matter, and our gas state of matter has an indefinite volume and no fixed shape. So when we talk about gases, remember, this is the part where everybody has completely broken apart from one another. They're flying around. So in the sort of state of matter of gas, we assume that basically the gas molecules are pretty much flying all around the volume of the container. So essentially they will fill the container uniformly. And as we'll talk about when we get to the sort of gas chapter, a lot of times when we're dealing with gases in an ideal situation, we think of the gas molecule volume as being the same as the volume of the container it's flying around it, because it's flying around and moving around and obviously causing collisions and pressures along the way there. And we oftentimes kind of overlook the volume of the gas molecules themselves and rather look at the container they're in because they are flying around and stuff like that. Gases can be compressed or expanded almost indefinitely. Again, that also involves pressure and volume. Gas water molecules are far apart and move freely and randomly. And that's what we see here in steam. Steam is our water molecules moving around and flying around. Now, when we talk about states of matter, although matter is separated by distinct or discrete units, attractive forces hold the particles together and give its matter basically an appearance of continuity. And basically what that means is there's really attractive forces are the strongest in solids, which is why they are rigid, a little weaker in liquids, and the weakest in gases. So there's two types of forces that we'll talk about, and we'll touch upon them in later chapters as well. There's what I refer to, for example, if I took one individual water molecule just by itself. So if I just like plucked out one water molecule, as we talked about earlier, this is held together by basically electrons being shared between the oxygen and hydrogen on one side and oxygen and hydrogen on the other side. And that's what is referred to as a covalent bond happening. And that is the bond basically between the oxygen and the hydrogen on one side and the oxygen and hydrogen on the other side. This type of force that holds together basically one individual molecule, this is what is referred to as an intramolecular force. Intra means within a molecule. So within one molecule, it is the force that holds together that particular one individual water molecule. Now, when we get a bunch of water molecules together, example of a bunch is I'm just going to actually draw two. And water, as we'll learn, is a polar molecule, which basically means when we look at water, the oxygen side of water is more negative, and the hydrogen side of water is actually more positive. And so for both of these cases, the oxygen would be more negative, hydrogen would be more positive. So one very important sort of concept for chemistry that comes about a lot in chemistry about how pretty much all molecules interact with other molecules that are the same or different molecules is a really basic sort of interaction of opposites attract. So in chemistry, much like in life, opposites attract, which means things that are positively charged and things that are negatively charged are attracted to one another. Things that are positively charged and things that are positively charged are repelled by one another, not attracted. And same thing, things that are negative and negative also are not attracted to each other. They're repelled by one another. Kind of like in life, right? Two positive people, two cheerful, who wants to be around that, right? Two negative people, clearly not going to get along. But, you know, they always say you find like your opposite, a positive guy, a negative person, right? They're going to be a good fit with one another. So it's the same thing in chemistry. Opposite charged things are attracted to each other. So the basic attraction between one molecule, like I said, with another one that's the same as itself, or even a different molecule altogether, is a basic attraction between positive and negative. And in the case of water here, when we get a couple of water molecules that basically get near each other, the positive side of one is actually going to be attracted to the negative side of another. And that is essentially what holds this entire water molecule together with this entire water molecule. As we'll talk about in a later chapter, that's what's referred to as hydrogen bonding. But that is also a type of interaction, which is known as a intermolecular intermolecular, all one word, I just wrote underneath, intermolecular force. And that is, again, the force that holds basically one entire molecule together with another. Now, these intermolecular forces are really important for things like melting points, boiling points, and how strong or weak something is. So, for example, if we have a substance that is held together by a really strong intermolecular force, that means it will take a lot of energy to break that molecule apart from another one of the same molecule. And if we're doing something like the boiling point, what that translates into is it's going to be a much higher boiling point than something that is held together by a very weak intermolecular force. So, for example, something like water has a relatively strong intermolecular force that it has held together, which means it has a pretty high boiling point of 100 degrees Celsius. Now, there are certain things that are, when they're together, are held together by very, very weak intermolecular forces. So, for example, if you light a Bunsen burner or even your stove or any type of barbecue or something like that, if you're familiar with, if it's gas-based, a lot of times those things are methane, propane, butane. Those type of things are held together by very, very weak intermolecular forces, which means if you just look at it and sneeze at it, it's going to break apart and go into the gas phase. And in fact, those things are actually gases under normal conditions. If you think about methane, propane, butane, it's basically how they naturally come as gases. And that's because they're held together super weakly, and it allows them basically just to go into the gas phase very, very easily. If you continue on and take something like organic chemistry, for example, a lot of organic molecules are held together by very, very weak intermolecular forces, which is why a lot of organic molecules are said to be what is referred to as being volatile, which means although they may be a liquid or something like that to begin with, they very, very easily can go into the gas phase. And that's why a lot of times when you're doing some type of work in, say, an organic lab, they oftentimes will put you in a fume hood because those things are very, very volatile and they could go into the gas phase, and you obviously don't want to inhale them. In addition, a lot of times those things are flammable, which is not great if you're using a Bunsen burner and you have something that's very volatile that's flammable as well. That's a bad combination that can happen. So when we talk about intermolecular forces, they are very important, and we'll cover it, I think, in a later chapter, but they're very, very important for things like why things have high or low melting points or freezing points or high or low boiling points. It's also responsible for, as we'll talk about in a later chapter as well, how things interact with one another, why certain things mix together, why certain things don't mix together. That's all revolves around these intermolecular forces. And it's a very important part of chemistry that we look at, and we'll look obviously more into that in some later chapters. Here are some common materials that are solid, liquid, and gas, and it's table from your book there. So as you can see, aluminum, copper, gold. We got alcohol, gasoline, oil, some air, butane, as I mentioned before, methane, nitrogen, and oxygen. Let's talk a little bit about ways to classify matter. Matter can be subdivided into several categories. We can have a pure substance, and a pure substance has a definite fixed composition. It could be either an element or a compound. So I think it's important to talk a little about some terminology here to make sure everybody sort of understands. As we talked about a little bit ago, elements are really as far back as you can go. So that is as far back as you can go. As we just talked about in a few slides ago, atoms, which are made up of protons, electrons, and neutrons, are basically the basic units of elements. Now, elements, as I said earlier, can be thought of as like the alphabet. I think there's still 26, I hope. 26 letters in the alphabet, but you could do different combinations of those letters, and you can make a bunch of different words out of those letters. And the same idea here, we have only so many elements on the periodic table, 110-ish or so, or whatever we're up to these days. But different combinations of elements, different amounts of elements that come together give us different compounds. And compounds are a combination of two or more atoms from different elements. So if you have a combination of two or more atoms from different elements, that is a compound. Now, a term that sometimes is confused by people is, in addition to elements and compounds, we also have our friend molecules. And molecules is a combination of two or more atoms together. So you may be saying to yourself, they kind of sound very, very similar. But there is a very important sort of difference between the two. And it is with the compound. Compound is two or more atoms from different elements. And that is the difference between a compound and a molecule. A molecule you can think of as really just a general definition of I have two or more atoms together. So a molecule does not need to be different elements. It can be two or more of the same element. It could be two or more of different elements. But a compound has to be two or more atoms of different elements. So let us see if we could sort of understand some of these differences. Elements, for example, things like hydrogen, oxygen, nitrogen, fluorine, chlorine, bromine, and iodine, for example. These mean that there are two of each of these guys. So, for example, if we look at hydrogen, it is two hydrogen atoms that are bound together. If we look at the nitrogen, it is two nitrogen atoms that are bound together, sharing of electrons. These guys are both what are referred to, and pretty much everybody up here, these are all what are referred to as being diatomic molecules. And a diatomic molecule means that there are two atoms. In this case, it's actually two of the same atoms. And because it's actually two of the same atoms, in addition to each of these guys being molecules, there are actually elements as well. Now, these six or so here, or seven, I think we got, seven are both elements and molecules. And by the way, that is how those elements come when they are by themselves and not combined. So if you have hydrogen by itself, it's actually hydrogen gas, which is two hydrogen atoms together. If you have oxygen, or sometimes referred to as molecular oxygen, it is two oxygen atoms together. And if you have nitrogen by itself, it's nitrogen gas, which is two nitrogen. Same thing with fluorine, chlorine, and bromine, and iodine. When they are by themselves, not combined with anything else, that is how they naturally come. They come as diatomic molecules. That is different than, say, if you had a piece of copper metal. If you had a piece of copper metal, it would just be what is referred to as being monoatomic. Mono meaning one atom. They come as ones, basically. So there are elements that are molecules, and those are example of the seven that are molecules. Now, are these guys over here, the hydrogen, oxygen, fluorine, chlorine, bromine, iodine, and nitrogen, are they compounds? So take a moment and think about it. Are they compounds? Is that a yes or a no? So if you think about what our conversation was about a compound up here, it is two or more atoms, which those meet the definition of different elements. They are not compounds. So they are not compounds because they only contain atoms of the same element. So elements can be molecules, but they cannot be compounds. So for example, if I had water, H2O, as we've drawn a number of times up to this point, water is a molecule because it is a combination of two or more atoms together. It is also a compound because it is a combination of two or more atoms together of different elements. So we have hydrogen and oxygen happening there. Is molecule an element? So take a moment there, yes or no. The answer is, Siri says, no. It is not an element because of the second example there. It is a compound, which means it has two different elements involved, which means it cannot be an element. So elements are as far back as you could go. Compounds are two or more elements together, which you could actually break apart into elements, but is as far back as you could go. And we have molecules, which again is thought of as really just a general definition of, do I have two or more atoms together? Those atoms, again, could be the same elements. Those atoms could also be different elements, but as long as they are two or more atoms together, that is the definition of a molecule. For example, if we had carbon monoxide here, which is CO, that is a molecule, two atoms together. That is a compound because it's two different elements together. That is not an element. By the way, that is also, just to put a note on it, that is also a diatomic molecule. So diatomic molecule doesn't necessarily mean it also has to be the same elements. You can have a diatomic molecule that are different elements together. Diatomic, again, just means that there's two atoms involved. Again, could be two of the same atoms like we have there with our elements. Could be two different atoms like we have with our carbon monoxide. Hopefully that clears that up. So let's talk a little bit about how matter is divided. Now, a pure substance is something that is basically has a definite and fixed composition. It's either an element or a compound, and it's basically just that substance by itself. So, for example, if we take just water by itself, that is a pure substance. If we take something like sodium chloride or salt, by itself, that is just a pure substance. We took gold by itself, pure substance. We took some iron by itself, pure substance. We took sand by itself, pure substance, whatever it may be. Now, when we take two or more pure substances and actually put them together, and let's just say here we made salt water, putting those two guys together, that is what is known as a mixture. So a mixture is a combination of two or more pure substances together. And the important part of a mixture is they retain their identity. So when you take two or more pure substances and put them together, they actually still maintain their identity. And there's two types of mixtures that we come across. One is a homogeneous mixture. In a homogeneous mixture, that is when we mix everything together and it appears the same throughout. So it appears the same throughout. Everything will mix together. Salt water is a very good example of that. If you take some salt, or like on the previous page, or sugar, and you put it with some water, some liquid water, it definitely will mix. And when you look at it, all this salt or sugar will pretty much dissolve. So it will just look like water, right? And it's kind of like the idea if you get some water out of the ocean, you just get the water, nothing else is floating around maybe in the ocean. It just looks like water. But if you ever tasted it by just sampling a little bit of it, maybe when you're swimming, you're like, wow, it's pretty salty. Because you can't see the salt, right? So it all looks the same throughout, and that's a homogeneous mixture. Heterogeneous mixture is basically when we have two or more substances that when you mix them, no matter what you do, you will still see different phases or different components. So for example, if you took sand and water and put it together, you can mix that thing as much as you would like. You'll never get that sand to dissolve in that water. You will always see the sand. Also, if you took some like metal and you put it in water, you can mix that all day. Put some quarters into some water, mix it all day. It will never dissolve. You will still see it. Much better sort of example, maybe like a chocolate chip cookie. You bake that thing up, you can still see the chocolate chips in there. So you do see different phases, is sometimes referred to, different layers. And that is basically a heterogeneous mixture. As it says here, ice floating in water is a two-phase system. Each phase is homogeneous, but overall it is heterogeneous because the ice is in a different phase. So you do see the ice cubes. Clearly, if you let the ice cubes melt, you now will have just a pure substance at that point. It would all be the same liquid water, but they are different phases. So ice floating around in, say, your glass of water is actually a heterogeneous overall. But again, if it should melt at that point, all become liquid water, you would be back to a pure substance and you would not have a mixture at that point. So a mixture, as I mentioned, is a combination of two or more substances, can be homogeneous or heterogeneous. And again, that homogeneous mixture is the same throughout. And when you mix them, they still retain their identity. And that's why it's really important to remember that. We'll talk about it here in just a second, but they basically will retain their identity. A heterogeneous mixture is one where, as I mentioned before, you could do as much mixing as you want. It will see different layers. Now, if you happen to mix different liquids together, you can get them to not mix. And if they didn't mix, you would end up with something like this, where you definitely would see different layers happening here. So we clearly see our different layering happening. They're definitely not mixing, and that would be a heterogeneous sort of mixture. Now, the important part of this is, as I mentioned, they are really only separated by sort of physical means. And what that means is no matter what type of mixture you got going on, you basically can get back the original components of that mixture by some type of physical sort of action. So an important sort of thing to maybe to talk about at this point is the idea of a physical change and a chemical change. And with a physical change, what you start with and what you end with are fundamentally the same thing. So a lot of things that are sort of physical states of matter, are physical properties of matter, are things like the state, solid, liquid, gas, things like boiling points, melting points. These are physical properties of matter. And when something goes through a physical change, what you start with and what you end up with are the same thing. So earlier we were talking about the idea of our ice cube going to liquid water, going to steam. All three of these things, although they are in different phases, they are all H2O, they're all water. These are all examples of physical changes. There is no chemical change that's happening here. It is water all the way through, just looks different. Same thing if you had like a peanut and you crushed it, and you had a bunch of little peanuts on the tabletop. They're all still peanuts fundamentally. It just looks different. And that's the idea of a physical change. What you start with and what you end with are fundamentally the same thing, just has some different sort of appearances. So states of matter, physical, solid, liquid, gas, very big parts of physical properties. Chemical change is different. What you start with and end with, go down, are fundamentally different. There's some type of chemical change that has occurred. There's some type of chemical reaction that has occurred. So for example, if you started with iron, you added a little bit of oxygen, a little bit of moisture through water, and you'll basically get rust, which is basically the fusion of iron, which is Fe, and oxygen together. Iron 3 oxide. So iron by itself, when you started with, fundamentally is now fused to oxygen in this process. This is a chemical change. What you start with and what you end up with is different. If you take some hydrogen gas and oxygen gas, they will come together to make water. Do a little balancing like we're in chemistry class here. There we go. And in this case, hydrogen gas and oxygen gas will make water. Once you have that water, as you might know, you could do a lot to it. You could throw it in the freezer like we talked about. You could put it on the stovetop to make some pasta. You don't get hydrogen gas or oxygen gas back when you do that, by the way. Otherwise, you'll never get to the pasta making part. If you start to boil water and get hydrogen gas and oxygen gas, boom, not so good. You get basically steam, which is still water. So that's a chemical change. The only way you could get the hydrogen gas and oxygen gas back from water is actually do another chemical change or chemical reaction. You actually run an electrical current through it and break it back into its elements. So for example, as we were also talking about, these are elements that end up as compounds. And if you wanted to, you would have to run an electrical current. And you could get back your hydrogen gas and your oxygen gas. These are gases at this point. And by the way, that's a chemical change, which is the only way you could do that. And then we would go from compounds back to elements in this case. And by the way, as we also talked about, that's as far as you could go. You can't break the hydrogen gas and oxygen gas into anything smaller. So that's basically as far back as you go. So in a chemical change, what you start with and what you end up with are fundamentally different than what you actually started with. It chemically changes to something different. The key there is you actually can't do any type of physical change to get it back. Like I said, you take the water, for example, if you make water, put it in the freezer, not going to get the hydrogen gas, oxygen gas back. You take the water and heat it up on the stove top there. You're not going to get the hydrogen gas and oxygen gas back. Again, it's going to go basically only through a physical change at that point. You have to do some type of chemical change to get it back. So why is it important in physical changes and chemical changes? When we talk about mixtures, regardless of the type of mixture that you make, you can get back the original components through some type of physical means. So when we talk about mixtures, we can basically get back the original components by doing some type of physical separation of it. We could boil it, we could filter it, we could do flotation or magnetism to it. Sulfur, for example, here in this picture, and if we put some iron on it, we can use a magnet to separate them out. The magnet obviously can grab the iron, but not the sulfur, and you'll be able to undo that mixture. Now, regardless of what type of mixture, you could always separate them out and get back the original substances. So let's talk about a couple of really important ways that you can get back those original sort of substances. One very common way of separating out a solid from a liquid is the process of filtration. So, for example, if we took some sand plus some water together, take a moment, is that a homogeneous or heterogeneous mixture? So take a second and think about it. And hopefully here, if you thought about it, the answer is it's a heterogeneous mixture. Again, no matter what you do, if you put those together, you're going to have some sand and it will be a heterogeneous mixture. So if you do a process of filtration, you could use what is referred to as a funnel. Here is why I failed art 9 times. We'll do my best funnel drawing. That's not too bad. It's good enough here. Let's see here. We'll do that. That is a world-renowned beaker I just drew it into. I know, close your eyes, you'll see the beaker. Usually if we do some type of funnel here, we put a piece of filter paper on it. And if we were to take this and pour this through here, we would see the liquid part come through. And obviously all that solid sand would get trapped up here. Sand up here, water over here. I then could take my filter paper, open it up, let it dry out. And I would have my sand back. That was one part of my mixture. And obviously here I would have my liquid water. So in this heterogeneous mixture, by a simple physical process here of separating out the solid from the liquid using filtration, we're able to get back both components of our mixture in their sort of original form. Now, if we had something maybe like, say, our salt water that we looked at before, and obviously, again, here, our salt water would be a homogeneous mixture. And if we take our salt water and we set up an apparatus here, it looks something like this, maybe a nice closed container, flask on both sides, connected by a tube that's really cold, and a nice closed system. And we put our salt water over here. And if I take my wonderfully drawn, again, Bunsen burner triangle, and I start to heat the salt water, what's going to happen to my salt water part? Take a moment, think about what's going to happen. I'll give you a hint. I'm underlining it. What should happen at this point is when you go and heat up the salt water, that actually will cause the water part here to start to evaporate. That's going to start to evaporate, right? And since that steam of water has nowhere to go, it's going to go through this tube, which is really, really cold. That's going to cause the steam to go through condensation that we talked about earlier. And before you know it, over here on this side, we are going to start dripping out some water over here. And if we continue to heat this up, eventually what's going to happen is all of my salt water on the left-hand side here, it's our cold tube here, all my salt water on the left-hand side is going to evaporate. And what that's going to leave me over here is just the salt. And obviously all of the water that evaporated had nowhere to go, which means eventually on this side, I will have all my water. And now through this process here, I have my water. Again, I take my salt, let it dry out a little bit. And now I have both the water and the salt, which was both parts of this homogeneous mixture, which if you remember, if you looked at it, you could not see the salt in there, but it is still there. It is actually trapped in the water network. So there's so much water molecules in there. You, with your naked eye, could no longer see the salt that's dissolved in there. But by getting rid of the water, now we are able to, once again, with our naked eye, see the salt that was dissolved in there and obviously get our water back in this case. So this is a really good way. This is what is sometimes referred to as distillation. Now, if you weren't interested, for example, in collecting the water, a very common procedure in lab, for example, is you would take what is sometimes referred to as an evaporating dish. And you would put your salt water in there, you would heat it up, and you basically would just lose the water as steam to the environment. So the water would just go off to the environment. And if you continue to do this, at the end, you would have just your salt left in your evaporating dish. So in the laboratories, we sometimes don't set up, especially in general sort of chemistry, we don't set up a big distillation apparatus here to trap the water and stuff like that. We oftentimes will just throw it into like an evaporating dish like that and let it evaporate off. And we don't really collect the water part of it. We just kind of collect the salt part of it, for example, in this example here. What are we really doing here? We're actually separating these things out by their physical properties. And if you remember, as I said earlier, one physical property is things like boiling point. So the boiling point difference between water and something, say, like sodium chloride, which is an ionic compound, versus this guy, which is a molecular compound. The water actually will boil at a lower temperature than the salt. So by using the difference in the boiling point, are these physical properties of these two substances in this mixture, we're able to separate out these mixtures by physical means. That's essentially what we're doing here. Sodium chloride is held together by really strong intramolecular forces, kind of the strongest forces you can have. You could actually heat the heck out of sodium chloride. It will never go into the gas phase. It will just start to melt. But water, you just need to get it to 100 degrees Celsius. And that's enough to get water to go from the liquid phase to the gas phase at its boiling point. And that allows it to be separated out from the salt, which will not boil at that point. So we're actually using a difference in the physical property of the sodium chloride and the water to allow us to separate these two mixtures out. So even mixtures that are homogeneous, like salt water, where you may look at it and go, I don't even see like the salt in there. Something must have happened. There must have been a chemical reaction. We can still separate them out by physical means because they do retain their identity. So what does that mean? That means that when we make a mixture, is a mixture a physical change or chemical change? That means that a mixture is a physical change. What we start with and what we end with are still the same thing. They just look different. So in the case of the homogeneous mixture, we don't see one component, but it's still there. It just looks different because it's really trapped between, say, all the water molecules and you can't see it. In a heterogeneous mixture, we can still see different components, so they're still there. So these are physical changes and not chemical changes. A chemical change would be something that we could not get back by exploiting a physical property like we did here in distillation, or even in filtration. We're exploiting the difference in size, right, and properties of those things. We're actually in filtration exploiting the difference between size of these two things. Water is small enough to go through, although if you ever look at a piece of filter paper, you may not notice it or be able to see it. You could think of them as, there's kind of like little holes, if you will. And water molecules are actually small enough to go through those and pass them. Sand, too large to go through those holes, and they get trapped, so they're not able to migrate through it. So we're actually using something like size differences, which is a physical property here with filtration to separate out the two components. So the take-home message here again is, regardless of the type of mixture, a mixture is really a combination of two or more substances that still retain their identity, which means it's a physical sort of change that's happening. And although it may appear that something chemically has happened, a chemical reaction, there is no chemical reaction that's happened. It's just a physical sort of separation. And we could still get back everybody by some type of physical means, filtration, distillation, magnet, right? Using some type of physical property to separate out those things. Take a look at a couple of examples here. Which of the following is a heterogeneous mixture?
Hello there. I told you I'd be back stopping by to say hello in these videos. Remember, this might be a good time to do some stretching. Stretch there, oh, stretch there, not bad. Do a little bit of stretch over there, a little bit of stretch over there. Oh, twist it again. Let me fix myself. There we go, there we go. That much better. All right, all seriousness aside, you want to make sure you stop? Pause these videos here. Although this example here may be a very short one, in future videos we will have ones that are more complex, and you want to take this time to do the examples yourself and not just watch the video straight through without working out the problems. Alright, just wanted to pop in and say hello and give you a little reminder of that. Alright, Mr. Professor Man, please continue on with our video. Only, of course, after you have finished working out the example.
So take a moment here and think about which one is heterogeneous. And hopefully you took soil is our answer. Soil is made up of a lot of things, dirt, rocks, whatever it may be. Obviously, copper metal is one substance by itself, grape juice, one by itself, gasoline, and baking soda is one compound by itself. Which of the following is a homogeneous mixture? All right, take a moment. And let's see here. The answer is maple syrup. Carbon dioxide is a molecule and a compound, so it is a pure substance. Mercury is an element, also a pure substance. Maple syrup has sugar, molasses, whatever else may be in your syrup in there. But it does look the same throughout, right, when you pour it. Concrete is a lot of things together, sand, rocks, and stuff like that. And Italian salad dressing, kind of oil and vinegar, right? Kind of mix it together. Some other spices and stuff in there that you could see. Filtration is a common method to separate out components of what type of mixtures? So take a moment here and see. Okay, so let's take a look. We got homogeneous mixture of two liquids. So filtration probably would not be so great for that. Heterogeneous mixture of two liquids. Not also be so good. Heterogeneous mixture of solid and liquid. That's sounding pretty good. And homogeneous mixture of solid and liquid. I'm going to go with C. Seems like the right one, as we talked about there. Again, like our sand and water mixture. All right, so that should be chapter 1. Not too bad here. It looks like it's going to be just one recording, so pretty good. We'll see you on the next one. So make sure if you do have any questions that you do ask. Other than that, have a good day, night, afternoon, whenever you're watching this. And we'll see you on the next one. Bye-bye.
Oh, hi. You're still here. You're still watching the video. I guess you're waiting for something to happen here at the end of the video. Let me think. How about the good chemistry joke to finish the video properly? I would tell you a good chemistry joke, but all the good Chem Lazy jokes are gone.